we're going to look at two more examples of comparison tests for infinite series. Here's problem A. We're going to determine if the series, the summation from 1 to infinity of 5 plus sine of n divided by n to the fourth power plus 3n, if this series converges or diverges. Let's take a look at part B. Here we want to determine if the summation from 1 to infinity of 5 plus cosine of n squared plus 5n plus 3 divided by n plus 1 converges or diverges. So again, let's review both parts of direct comparison test or comparison test. Suppose that the series from summation from n equals n sub naught to infinity of a sub n and n equals n sub naught to infinity of b sub n. So if these are two series with positive terms, so that means a sub n is positive for all n and b sub n is positive for all n. And b sub n both positive. So here's the first part of comparison test, is the convergence part. So if the b sub n series converges, so n equals n sub naught to infinity of b sub n, if this series converges, and the a sub n terms are less than or equal to b sub n terms, then the a sub n series also converges. And then the second part of comparison test, the divergence part, if the b sub n series diverges, and b sub n terms are less than or equal to a sub n terms, then the a sub n series will also diverge. Okay, and let's take a look at some of the inequalities involving sine and cosine. We know that for any n, sine of n is between -1 and 1. Similarly, for cosine of n, but we can extend that, namely that we have sine of anything that is defined. So if you take any expression, any function of n, as long as it's defined, is always below or less than or equal to 1 and greater or equal to -1. And similarly for cosine of anything defined, it's less than or equal to 1 and greater than or equal to -1. So let's solve the two examples now. Summation from 1 to infinity of 5 plus sine of n divided by n to the fourth plus 3n. So we'll start with the denominator. N to the fourth plus 3n is greater than just n to the fourth, which means that 1 divided by n to the fourth plus 3n is less than 1 over n to the fourth. And of course, everything is positive. Let's multiply everything by 5 plus sine n. 5 plus sine n is a positive number. Therefore, it will never switch the inequality or reverse it. So 5 plus sine n over n to the fourth plus 3n is less than 5 plus sine n over n to the fourth. And we know that sine of n is less than or equal to 1. So this is less than or equal to 5 plus 1 over n to the fourth, or 6 over n to the fourth. We now label the sequence 5 plus sine n over n to the fourth plus 3n as a sub n, and 6 over n to the fourth as b sub n. And we see that a sub n is smaller than b sub n. So now let's look at summation 1 to infinity 1 over n to the fourth. We know that this series converges because it is a p-series with p equals to 4, which is greater than 1, therefore it converges. If we multiply this series by 6, so this will turn into our b sub n series, which is summation from 1 to infinity of 6 over n to the fourth. Multiplying a converging series by a constant keeps it converging. So the series converges also, b sub n series converges. And now we can bring the series in. So we have the summation from 1 to infinity of a sub n. Remember, the a sub n series would be summation from 1 to infinity of 5 plus sine n divided by n to the fourth plus 3n. This series summation is less than the summation from 1 to infinity of 6 over n to the fourth, which is the b sub n series. We know that this series converges, and therefore we make the call here by using comparison test. The summation from 1 to infinity of 5 plus sine n, which is the a sub n series summation from 1 to infinity of 5 plus sine n divided by n to the fourth plus 3n converges by comparison test. And let's take a look at part B. In this part, we have a summation from 1 to infinity of 5 plus cosine of n squared plus 5n plus 3 divided by n plus 1. So once again, we're going to start with the denominator n plus 1. And instead of saying it's just greater than n, we want to say it's less than or equal to n plus n, because the second n is greater than 1, so that's 2n. So n plus 1 is always less than or equal to 2n, and therefore 1 over n plus 1 is greater than or equal to 1 over 2n. That's the key to solving this problem. So we're going to multiply both numerators by 5 plus cosine of n squared plus 5n plus 3. So we have this inequality, 5 plus cosine n squared plus 5n plus 3 over n plus 1 greater than or equal to 5 plus cosine n squared plus 5n plus 3 divided by 2n. But remember, cosine of anything is greater than or equal to minus 1, so this is greater than or equal to 5 plus negative 1 over 2n, which is 4 over 2n, which is 2 over n. And now let's label 5 plus cosine of n squared plus 5n plus 3 over n plus 1 as a sub n, and 2 over n as b sub n. So here a sub n is greater than or equal to b sub n. Now let's recall that the series 1 over n, summation of 1 to infinity, 1 over n, diverges because it is a harmonic series. And multiplying a divergent series by a constant such as 2 will not make it converge. It'll keep it divergent. So the b sub n series, namely 1 to infinity, sum 1 to infinity of 2 over n, also diverges. And now we can make the call, summation 1 to infinity of a sub n, which is our series, 5 plus cosine n squared plus 5n plus 3 divided by n plus 1 is greater than or equal to summation from 1 to infinity of 2 over n, which is our b sub n series. And the b sub n series, we know it diverges. And the a sub n series is greater than the b sub n series. So by the second part of the comparison test, the divergence part, we can now conclude that the a sub n series, summation from 1 to infinity, 5 plus cosine of n squared plus 5n plus 3 over n plus 1 diverges by comparison test.